This video is all about gases and gas variables. So you might be wondering, well, why do we need to study gases? Gases have really predictable behavior. We have these laws and equations that describe that predictable behavior. But first, we just want to talk a little bit about them and their variables. So what are some common examples of gases that we'd use in everyday life? How about inflating a balloon? In inflating a balloon, we add more and more gas to that balloon and we increase its volume. Every time we're breathing, we're utilizing gas laws and gas variables. When we inhale, what we're doing is increasing, the volume of our lungs, and that decreases the pressure inside them and causes air to enter our lungs. And so, if you go into the health sciences or the allied health sciences, there's lots of use of gases, right? Sometimes patients need oxygen. Sometimes in the dental field, we use gases to sedate. So there's all different uses of gases that are really common in everyday life. So it's important to know a few things about how the different variables of pressure and volume and amount of gas are calculated. Another example is a combustion engine. In a combustion engine, there's really rapid expansion of heated gas in the firing portion of that, and that drives the piston. When that rapid expansion occurs, the piston moves, goes down, or that volume has to increase, and that drives and pushes the piston. So we have a lot of examples of gases really in our everyday life. So there are 11 elements that exist as gases. And so, well, what are some of those elements that we need to know? Boy, where I have them. Oh, okay. Sorry. Clicking away. So the noble gases, helium, neon, argon, krypton, xenon, and radon. So we call those gases, and they really are in the gas phase at room temperature. All of our molecular gases. So for example, hydrogen, nitrogen, oxygen, these diatomic gases that like to come in twos. The halogens like fluorine and chlorine. So those are really our 11 elements that exist in the gas phase that we work with a lot. Okay, so I promised we'd get into gas variables next. So what are the key gas variables? Pressure, volume, amount of gas that we call N, and temperature. Okay, so pressure's unit's going to be P. Pressure is just the force exerted on a given area, so force per unit area. Some units of pressure can be the Pascal. This is our SI, or International Unit for Pressure. It's really a very small unit. A Pascal is a Newton per meter squared. We actually most often use atmospheres. That's what we use in chemistry, and an atmosphere is 101,325 pascals. And so I've got a little image here to show you how an atmosphere would be measured. 1 atmosphere of pressure is the force due to gravity of a meter squared column of air through the whole atmosphere is 1 atmosphere of pressure. So air pressure at sea level is about 1 atmosphere. Here in Minnesota, it's almost an atmosphere. We are almost at sea level, not quite. It's usually a little less. And another unit for pressure is the torr. And so torr can be used in barometers, for example. There's a picture of a mercury barometer over here. And so a torr is about the same as a millimeter of mercury. So we'll say, 760 millimeters of mercury is about the same as 760 torrs, and that's equal to 1 atmosphere. So 760 millimeters of mercury is about 760 torr and equal to 1 atmosphere. So the air pressure pushing on this column of mercury at sea level is 76 centimeters, or 700, and if we convert the centimeters to millimeters of mercury, we would have 760 millimeters. So 76 centimeters equal to 760 millimeters. And that's why 760 millimeters mmHg, millimeters of mercury, is equal to 1 atm. So again, we have pressure. That's going to be our gas variable P, commonly measured in pascals, ATMs, or torrs. We like to use ATM a lot in chemistry. And then we're going to have V for volume, and that's is typically in liters. Volumes can be in milliliters, for example, but usually in liters. And then we're going to have amount of gas, and that's typically measured in moles. I think of amount, or N, we use N for moles, to be like N for number of moles. That's how I relate to it. If you think about the letter M, it's pretty overused. M already stands for mass. As a unit, M is meter. M is tired. And so we needed something else. And so N, I think of as N for number of moles. So if you want to write that, I don't know, something like this. N for number of moles. So N is going to be moles. And then T just for temperature. So the temperature of a gas, using the gas laws, always needs to be expressed in units of Kelvin. So we do all our temperatures in Kelvin. The reason that we don't use Celsius or Fahrenheit, for one thing, we don't want to have any zero temperatures. We would be multiplying or dividing by zeros, and those would give us nonsense, zero answers, and so we can't do that. Temperature is not the same as heat. Temperature is a measure of, on average, how fast are the particles moving? What's the average kinetic energy? So on average, how fast are molecules moving? Average kinetic energy. So temperature is a measure of average kinetic energy of particles. Heat is about transfer. Heat is the transfer of thermal energy from a hot body to a cooler one, from something that's hot to something that is colder. Okay, so temperature is really telling us about, on average, how fast are these particles moving. So it's a measurement of average kinetic energy of molecules in an object or in a system. And our SI unit of temperature is Kelvin. So we got to sit back and talk about temperature scales for just a little bit. So 1 degree of Fahrenheit is not the same as a Kelvin or Celsius. A degree or an increment in Kelvin or Celsius is the same, but a Fahrenheit is 5/9. So Fahrenheit is 5/9 the Kelvin or Celsius, which those two are equal. That makes for some really annoying conversions for Fahrenheit, let me tell you. So Fahrenheit is Celsius temperatures times the fraction 9/5. And then once you've done that calculation, add 32 degrees. Celsius, you just have to do in reverse, right? It's Fahrenheit minus 32, and then you do that, so that's in parentheses, and then you multiply times 5/9. You've just got to do this whole process in reverse. Now, Kelvin is just the Celsius temperature plus 273, because Kelvin sets the 0 point at what we call absolute zero, or 0 Kelvin. So to get from 0 Kelvin, you're just to 0 degrees Celsius, you're just going to add 273. Whereas the bottom, bottoming out, absolute 0 on Celsius is negative 273 Kelvin. Now, some people do 273.15 to be more precise. I tell you, I sometimes drop the 0.15. As I'm kind of doing here. It doesn't always make a huge difference in some of our calculations. So I'm not always in the habit of putting the exact 273.15. I just thought I would warn you of that up front. I might put it and I might forget and drop it because you can usually approximate without the 0.15. Okay. You might wonder, where on earth do we get this Fahrenheit scale from? It's hard for me to justify. It's got to be one of the things about science I don't really like. I'd rather stick with our metric, Celsius and Kelvin. It was developed by Lord Fahrenheit. That's where you get the name. He set his 0 at, interestingly enough, the freezing point of salt water. If you just kind of want to understand why we're stuck with this. It does help me a little bit to understand. So sorry, that's freezing point of salt water. That was his 0 Celsius point. And then, he meant to have kind of his 100-degree point at body temperature. But apparently he used the body temperature of his wife, and so she must have had a little bit of a fever or something instead body temperature ended up at 98.6. It ended up a little bit below 100. So I think that's kind of interesting, that his wife's body temperature must have been 100 F. You just like go, really? You can't even make this stuff up. So anyway, we know it to be lower at 98.6 true body temperature, not the body of someone's wife. But anyhow, if you're kind of curious as to why we ended up with this system, well, here's kind of what it's based on. 0 Kelvin is called absolute zero because it's the lowest theoretical temperature. So in developing the Kelvin scale and looking at gas laws, we could come up with, as chemists, a theoretical lowest possible temperature where, in theory, molecular motion would really stop. So it's kind of cool to imagine reaching that. But we like our temperatures to be in Kelvin because there's no negatives on the Kelvin scale. And we start with 0 Kelvin, with the 0 on the scale being truly representative of 0 energy. And so doubling your Kelvin temperature really doubles your heat energy. You don't end up with any negatives. You don't end up dividing by 0. So Kelvin is kind of our gold standard here going forward for our problems that we need to be in Kelvin. So if we've got Fahrenheit, we'll have to go to Celsius and then get that Celsius to Kelvin. If we're given Celsius, well, we'll just have to add 273 or 273.15 if we're going to be precise. That's going to be our goal. Okay, let's just try some unit conversions with these variables. The barometric pressure on a sunny day in March is 29.85 inches of mercury. Convert this pressure to units of millimeters of mercury and ATMs. Okay, so let's just write down our known. We know 29.85 inches of mercury. That's a known, and we'll just put that over 1. And so what we want to do is say to ourselves, okay, well, if we go back a slide or two here, we can catch a little conversion factor that we need. Oh, right here. We see that 29.92 inches of mercury is the same thing as 76 centimeters of mercury, which is the same as 760 millimeters of mercury, or 760 torr. Oof, let's rewrite those conversions. So we just kind of have them over here. Let's write 760 torr is the same as 760 millimeters of mercury, and it's actually the same as 29.92 inches of mercury. By the way, all those are also equal to 1 ATM. Oh, you can see why I like that better. It's so simple. But an ATM is the same as 760 torr, 760 millimeter of mercury, and 29.92 inches of mercury. Okay, so that's going to be our conversion of the moment. 29.92 inches of mercury to get rid of those. And it says that we want to be first in mmHg, millimeters of mercury. So we'll say in 760 millimeters of mercury. Cancel out inches of mercury, and we'll get 758.2 millimeters of mercury. Now the next thing we want to do is get that into ATM. So this was our first answer, but we can just set that as a known over 1 and get rid of millimeters of mercury, and this time instead get to ATM. One easy little ATM in 760 mmHg, or millimeters of mercury. So this time we divide by 760, and we should get 0.9977 ATM. Okay, so we're done with these little pressure conversion practice. How about a temperature conversion practice? The average body temperature of a human is 98.6 degrees Fahrenheit. Convert this to Celsius and Kelvin. So oftentimes, you'll talk about temperature in Celsius in a nursing or medical field, and you might be so used to hearing about it in Fahrenheit. So it would be good to know this one in Celsius. Okay, so what are we going to do with our Celsius? Well, first, to get to Celsius, rather, we're going to take our 98.6 Fahrenheit, subtract 32, and then multiply it by 5/9. So we just go back to that formula, pick the right one, plug that all in, and we should get 37 degrees Celsius. So that's actually a really great number to have in your back pocket. If you're interested in any medical profession, is knowing body temperature in Celsius is at 98.6. That's Fahrenheit. Know that it's 37 Celsius. Okay, and how about converting to Kelvin? All we do is take our answer in Celsius and add 273, or 273.15 if you're feeling pretty precise. And when you do that, you should get 310.2 Kelvin. Now, since we're adding, we go by decimal places, and so we end in that tenths place in terms of sig figs. So hopefully now you feel comfortable with the units that we're going to use for gas law problems, and also how to do a few conversions with them.